Sorry, I have a weird sense of humor.
So they only last 30 years.
20, 30, yeah. We're live again. And okay, so a couple of points. Yes, I'm doing this, and we're working our way through a number of lectures. We now have next Wednesday, Monday, of course, there's no lecture anyway. We now have next Wednesday in the can. We have the following Monday and Wednesday in the can. So we're now shifting way out almost into February, I think, and we'll continue to do that today and tomorrow, so that you have a total of 8 lectures, 9 if you include last Wednesday, ready to just be able to watch and review. Hopefully you guys will join me again tomorrow at 9. I can't imagine doing this without an audience. And I really do like having a large number of you guys here. I will review so that even if you have to miss 1 or 2, that's fine. You may hit the alarm clock at 9 in the morning and say I'll come to the 10:31. That's fine. Don't worry, I'll get you up to speed. Yeah, so I like the fact that you're all here, and I admire the fact that you are willing to come in for an entire Saturday and hopefully most of Sunday too to do this. It makes my job easier, more happy, and nicer, and I hope it gives you some more opportunities to ask questions. Now, I know you're going to have questions, and I know the folks watching this on tape are going to have questions. I have high hopes for the thread, for the forum on e-learning. I think that if you're watching this, as you've asked questions during class and during the break, I've tried to bring them into the lecture. I'd like to continue doing that somehow. There's 2 ways of doing it. One is you can be patient and wait till I get back, and I don't recommend patience. I think impatience is as much a virtue as patience is. And so what I would do is I would go on the forum and I would write a note saying, that idiot McFarland left off a minus sign on the Gaussian in the frequency domain. Is that right or wrong? And then somebody say, yeah, it was just a mess up. Or else, what is the difference between a discrete time signal and a digital signal? That's a little harder for me to explain on the forum, but at least I can give you some bullet points and address it in more detail when I get back and be ready for it when I get back. And the nice thing about that instead of an email is 2 people asked me that question, one right after the other. And so if it's done online, if you have the question, likely as not somebody else in the class has the question too. And so let's just get it. Let's just be public and get it out in the open. You should never ever worry about not knowing something. You guys are brilliant. You guys are hardworking. Otherwise, you wouldn't get this far here. It's perfectly reasonable and sensible to say, I'm smart, but I just don't know that particular thing, or I'm just confused. Get it out in the open and let's get it solved. Okay. Let's make that right off the bat. Okay.
Earlier during the video session, you said you wanted to talk about the homework on the video.
Oh, thank you. Yes, I do. I had a question. Somebody didn't come to the Monday class. Maybe they were transferring in late and they missed the long preamble of the logistics of the course. What I'd like you, if anyone's in that category, go to the e-learning or my webpage and find the syllabus. The specific question was the homework, and I do agree. I have a very strange homework policy. I don't collect homework. But I do give homework, and I do count homework a heck of a lot in this course. All the homework problems from all the chapters that I'm assigning are already online as a list of questions from LaTeX 4, LaTeX 4th edition, the newest edition. And then I also have the solutions, and I have the published solutions, but I also have much better the TA solutions. In some cases, I've got 2 TA solutions for one problem, and those I've tried to make. I've tried to beat on the TAs to make them much clearer, much more much less terse, much neater. And so you have reference. You have that reference, but please don't use those. Solve the problem so that you know the solution and you understand it fully. So you don't need those. You maybe just look at them to check, because when you come to the exam, there'll be maybe 3 problems on the first midterm. One of those problems is going to be a homework problem from chapters 2 and 3. And you'll be looking at that homework problem with closed notes, no calculator, only a pencil and paper, no book. And so if you've done your job on that homework, that's an easy 10 points. That's an easy 10 out of 30 points. And if you add 10 and 10 and 10, you see that the homework in this class is worth 30% of your grade. 30% of your grade. Whereas if you, in other classes, because of bookkeeping, the large amount of work for the TAs, and not least which maybe some academic dishonesty issues we've had in the past, homework only counts for 5 to 10%. But in this class, it's absolutely huge. So my homework policy is huge. You can imagine the difference of 30 points is the difference between a 90 and a 70. It's the difference between a 60 and a 30. So you will be knocked down huge letters grades, or conversely, you have a huge head start if you do what I call the effort work, which is the homework in a way as possible. There is one. While we're on the subject of the exams, there'll be plenty of time once I get back to set the date of the exam. I'll give you 2 weeks warning. There'll be some review. There'll be plenty of interaction for you to come up to speed again. Don't worry about that. You're not going to come back and immediately be hit with an exam. There'll be a ramp up. Even if it means that the midterm grades get to you a little bit later, I hope that does. I don't think that'll happen. Maybe there's a slightly elevated risk of that. One thing you will have on the exam will be this sheet of paper. Will be these sheets of paper. And if you go to the back of Lati Appendix E, there's this sheet of paper, and this sheet of paper has. It has the L'Hopital's rule, a Taylor series, power series. Which are good for expansions, some summations, complex numbers, trigonometric identities, which are big ones, some integral tables, and some integrals. So there's just some math facts that are found in this particular Appendix E, which you have in the book, and I Xerox and give it to you. If you write on it, as this person did, I will actually try to keep that and actually try to grade it, but I don't recommend you counting on that. So this is just scratch paper. If you don't write on it, I went to graduate school in Oregon where we're all tree huggers, and so I try to keep those separate and use them again. No real reason to, other than, again, good for the environment, or at least I think it is. Okay, is that a decent enough answer for you? Okay, so last time we started down the, again, I don't want to go into great detail of the review, but last time I was review of linear time invariant systems, which we sort of did. We did convolutions, at least one half in the discrete time case, and we didn't get to Fourier series, sorry. But the march goes on. And we'll do convolutions in the continuous time case today, and we'll start in on the Fourier series for what we are today. The digression on quantization, analog digital discussion, the convolution, the superposition, and an example, a very simple example done about 17 different ways of bookkeeping. And I hope you look at all that in hindsight as extremely tedious and probably not worth the price of admission. I hope, but you never know. You may value that, and that would be good too. I also sprinkled in a little bit of some discussion of what constitutes. We classified signals. You can also classify systems by looking at the delta function response, among others. And so this particular case was a causal system because it began at 0. The delta function response began at 0. For a non-causal system, it would respond ahead of the input. Anticipation. A person can flinch when a blow is coming, right? But an inanimate object can't. Okay. And even if it can, you can use, what usually that the case is that you're setting the wrong 0, or you've shifted the 0 for a different convenience. Okay, which can happen, and then conservation of energy as well. Now, we had a convolution sum that we spent a lot of time with last time. This time we're going to spend a little bit of time at the beginning on this convolution integral for continuous time case. And I don't think I need to go too much into detail on that because it comes right out of the discrete time case. It's the same principle. It's just continued in the continuous time instead of discrete time. And so I'm going to jump right to an example. But just for the purposes of having all this nice and organized, convolutions of continuous time signals. So I have an input x of t into a linear time invariant system here, and it's characterized by a delta function response of h of t. And I want to know what the output y of t is. And I know that the y of t is the convolution of x of t convoluted with h of t. And that's also equal to h of t convoluted with x of t. So the order doesn't matter. And that's an interesting thing. If I can just digress a little bit, where there's a colloquial term used when I say, boy, that was a really convoluted lecture, right? Or that was a really convoluted presentation. I usually mean that things were muddled together. And so this is not too far off that fact. I can't distinguish on the output. I can't distinguish what the input is from the output. I'm sorry, I can't distinguish what the input is from the delta function for the system response. Those two, whether one's an input and the other is a delta function response, or one's the delta function response, the other is the input. I've lost that information. So this is a drastic shuffling of that information. And so you can think about even the generic or colloquial or casual term convolution. It actually bears itself out in the mathematics, I think. And then so that's kind of a interesting case. Now the convolution sum becomes a convolution integral, as was very nicely pointed out. Tau becomes the dummy variable. That's the shift in here. And so instead of the summation, I've got an integration over all time. Integration over all time. And that's the product of these two functions. So again, if you look at this minus sign here, that minus sign means a flip. And then you drag one signal across the other, multiply, and add. Multiply and integrate. And we did this one example 3 different ways. The last way, which miraculously worked out thanks to some help from you guys, showed exactly that procedure in the discrete time case. And so that's what we're going to do for our convolution example now. Okay. Now the example that we showed was a decay and a square pulse. So why not? It doesn't really matter what we do. There's something both good and bad, pretty and impractical, or not, about considering exactly the same, or almost the same waveforms. So I've got a linear decay. 3, 2, 1 was the decay for h of t. And this is time axis, and this is the maximum is b. I didn't draw that very well, I apologize. And the length of time, that's b in volts, and this b happens to be in seconds. Not a very good notation. I warn you about that. So clearly some mathematician, I had my mathematics hat on instead of my engineering hat when I was thinking that. And then x of t. Is a pulse and it has a duration of a. And the way I've drawn it, and the way I'll calculate it, but it's not necessarily, it's not necessary. It's not necessarily necessary. How's that? A is greater than B. But, and what I would recommend if you wanted to, tonight, of course, when you're, not going out on a Saturday night, you can do the other case and think about it that way. or do other examples. Now, the first thing to note is, okay, I've got these sketches, and I'm going to be doing these integrations, and so these integrations are going to want an analytic form, a math form, for these sketches. So I've got to take a little bit of time before I get started, and I've got to come up with the representation of these. So I need an expression for h of t, and I need an expression for x of t. The expression for x of t is easy. It's a step function that goes on. So u of t. And a step function that turns off or goes negative that's delayed. Okay? So that's one way to represent that. And then what's nice about that is I know the step function is a representation of 1. And I like that a little bit better than using the pulse waveform that Lottie has, because I'm sliding that through, and it'll be nice to make the quick connection to 1. So that's the expression for x of t. Now, this guy h of t, it seems to me that it has three regimes that I want to be careful about. It's causal. It's a causal system again. So the delta function happens at 0 to generate h of t. It happens at 0, and there's nothing going on with that h of t before the delta function hits it. And so it's causal, so h of t is equal to 0 for t less than 0. Okay? There's also finite impulse response. It's also a finite impulse response, which means that if a delta function comes in, the impulse function is on for a while and then it turns off. It goes bang to 0. So it's not. It's a finite impulse response, and so it's 0 again for t greater than b in seconds. Causal, and I probably didn't emphasize these guys enough, but I'll label that as finite impulse response, FIR. Okay. Seems like you guys are fairly comfortable with IIR and FIR.
If the amplitude of your response drops below the noise level, can you consider it an FIR?
Yes, absolutely. Even if it doesn't, and your noise is determined by what you care about, you can approximate it. So remember this I've introduced both of these as an approximation to an exponential decay. A bad approximation to an exponential decay, where bad is sort of is a judgment call. Okay, we could do better. Do we need to? I don't know. Probably, but it's from an engineering perspective, this will get me something. Okay, so okay. So now I need something. What's going on in between, and the region that I care about is going to be after 0. And before b. Okay? And these equal signs, greater than or equal signs, less than or equal signs, that's something that you'll want to kind of think about a little bit. And in this case, we'll get a function that goes to 0 right at that point. And so whether we approach it from this point or this way, we'll get the same number. There's a slope discontinuity, but not a functional discontinuity. Okay, and so again, this signal doesn't exist, right? It's an approximation of something. Okay, and so truth is in the physical realization and not in the mathematical expression, or maybe truth is in the math and not in the physical. I don't know. That's philosophy. Depends who you talk to. This is a straight line, so we're looking at y equals mx plus b. A bad notation. Y equals a slope times time times an intercept, and the slope is -1, and the intercept is b. So this will be at b minus t. So I had to do some curve fitting. I had to do some curve fitting for that. Okay? So to get that was not just b minus t. What I really did was I said I'm going to take a polynomial, a Taylor series, and I'm going to fit the Taylor series to that thing, and I'm going to fit term by term by term. At t equals 0, it's b, and then at t equals b, it's 0, and that gives me my two equations, two unknowns for those things. So I don't want to trivialize. I hate it. I used to hate it when professors just say, "Oh, and it's obvious b minus t." Well, I'm giving you some background that I wrote down 4 or 5 lines of math to get that, and I would encourage you to leave some space in your notebook to get it as well. Okay, so it's not nothing that nothing that you should snap right out of your head right off the bat. If you do that, you'll get close, but not right. And so I encourage you to do it more carefully. And then, of course, what we're going to be looking at is y of t is equal to the convolution of x of tau h of t minus tau d tau. And we will apply the flip and drag method. And so I could do this either way. I'll do it. Let's see. I'm going to flip h of t, and I'm going to drag h of t through here, which I think is that's different the way I did it last time, or maybe not. I don't remember. But nonetheless, I'm going to do it this way. And if I look at this, remember, a is greater than b. I should have drawn this a little bit, I've got a few cases to consider. This is before time starts. So this is, let's see, this is going to be t, and this is going to be t minus b. Okay? So this is for t less than 0. I'll call this case 1. Case 2 will be any time that t is greater than 0, but the tail end hasn't quite overlapped it yet. So this is case 2. Case 3 is in there. So the whole pulse is exciting the system. Case 4 is when the leading edge of the triangle pulse has stopped exciting it, but the trailing edge is still coming through. And then case 5 is sitting out over here. Everything's quiescent again. And the only thing difficult about 1 and 5 are the unit, are the limits. Okay? So for t less than 0, this is case 1, the integral is equal to 0. Y is equal to y of t. Okay? And for case 5, this is t minus b. And so this occurs at t minus b. This point here, bigger than a. That's the integral for 5, and that's equal to 0, and that's equal to y of t. There, we are 2/5 of the way through the problem. And the only tricky thing about that is understanding these limits. Okay? And so when you flip it, and when you walk through in time, this leading edge is going to be t, and then that's whenever it stops going. Okay? So take a minute and just take a look at the at where those limits are, and get comfortable to the point where you can do that without me telling you what it is. Right? I'm trying to obviate myself. I like you guys dearly, but 20 years from now, I don't want you to be calling me up and asking me for these. Okay? So you have to do this without me. Okay? Call me up for other things like beers and stuff, but don't. Not for that. Okay? Integral number 2. Integral number 2. The limits of integration will be the first thing that we consider. And this is t. And we don't really care about what's going on in this tail here, right? Because there's no overlap. There's no multiplication. We're sliding this through. We're multiplying and integrating. We're sliding this through. We're multiplying and we're integrating. That's the nature of the convolution integral. Multiplication and integration. And in this case here, for case number 2, that's a big old 0. So the lower limit of integration is this point here. And that point there is what? T equal what? 0. Very good. And this guy, and then beyond this guy here, it's 0, because the triangle pulse hasn't excited that yet. So what's the upper limit? T. So whatever this works out to be, this will be for t greater than 0, and for t minus b will be less than 0. The things that I multiply together is going to be 1. That's the pulse. I'll multiply that. I'll put that in explicitly. Hopefully that won't confuse you. But it's in blue, and the original pulse was in blue, so maybe that'll help. Maybe not. I don't know. And then the function is b minus tau. There. And this is tau equal to 0, tau equal to t, because I have to worry about dummy variables here. And then this is integrated across d tau. And if you think about it, that kind of makes sense, because whatever goes on in here in tau, you don't care about, because you want y of t. You don't want y of tau. You want y of t, what's going on in real time. So tau is just your dummy variable. I've seen that as a point of confusion with students, and that's why I kind of wanted to bring that up too. Okay? Is that a difficult integral to do? Is that a difficult integral to do? No. No. So in this case, convolution of 2 simple signals are going to be nice. If they were 2 cosines together, what the heck are we going to do there? Pardon? Trig identities. Another way to approach it is to move it into complex exponentials and use the exponential notation. Okay. So if you've got sines and cosines in there, or exponentials in there, you've got to wrestle them off in different ways. What if you have a Gaussian in there? Are integrals of Gaussians easy to do?
It's self, right? It's kind of like the...
Not quite. The Fourier transform of a Gaussian is a self. But what happens if I integrate under the bell curve or under the normal curve, normal distribution? I can't do it. I need to look at, it's the error function. And I need to run to a lookup table. The best I can do is write it as an error function. And I have a notation for that, but that's all that is. A code is press that key on your calculator, or code that into MATLAB, or run to, in my day, we had these CRC handbooks of mathematical tables and formulas. and we would have to go to those and open them up and write down. This was all handwritten on parchment from monks in Ireland, and we'd find the table entry, and we'd hope that the person who had typed that in hadn't made a mistake on that particular line. So but it's still a lookup table, and it's the old-fashioned version of pressing a key on your calculator. All right, I digress, and I apologize for that. BT minus t squared over 2. Actually, I don't apologize for it because, in fact, the error function is going to pop up when we do noise. Okay, when we started on looking, we're going to do noise. It should not be surprising that Gaussians come out of noise, the central limit theorem, Markovian processes, so on and so forth. And so dealing with stochastic processes is going to give us Gaussian processes, which is going to give us error functions when we try to understand the amount of noise in a particular segment. Just a little heads up, something to look forward to. Way off in April or even May, depending on how late we go. I've forgotten. Well, anyway, while I was babbling on, I was also doing the integral. So b d tau is giving me a linear function. Tau d tau gives me a quadratic function. And there's your answer. There's your answer for case 2. So where we are... Oh, sorry. Where we are is we've done case 1, case 5, and case 2, and we've got 2 more cases to do. Okay? So I guess I hope you won't mind if I do this a little bit out of order. Case 4 is also fairly simple. Case 4, I don't care about what happens after A. And I don't really care about what happens after this point here. This point here is t minus b. So my limits of integration, what's my lower limit of integration?
T minus b.
Excellent. What's my upper limit of integration? Good. And I'm doing the product of the step functions 1 multiplied by b minus tau, d tau. You see that's exactly the same integral as I had before, but now my limits are a little bit different. Let's see, this is for t greater than a. So case 4, this is t and this is a. So when t is greater than a, and it's also when this point here, which is t minus b, is less than, when this point here, t minus b, is less than a. Okay? So the bookkeeping that goes on out here is just as important and similar to the limits of integration. Okay, the bookkeeping part of this problem is now of case number 4 is now done. Okay, not trivial. We've got to get all those lined up. It's not trivial, but it's done, and it's done with the help of the careful figure and careful labeling. And so now we shift gears and we say I've got an integration to do. That integration I can do without too much thought, but if I have a problem, I can go to my integral tables. And if I can't do the integral table, then I'm stuck with numerical approximation. But in this case, I can do it. And so this is equal to t squared over 2, the same t squared over 2 as that guy was, minus 2bt minus 1/2 a minus b quantity squared. That's the answer. And it looks to me like I did some simplification to get there. So what I'd encourage you guys to do is to do this to leave a couple of lines underneath this and fill in the details. Do that maybe on Wednesday or something when one of our classes rolls around and I'm not here and you're missing me and so you go in and do it. Or you can do it tonight before you forget the significance of it. But just a few details. I think you can all imagine yourself doing it, and I think you actually can all go ahead and knock that off. All right. We now have case number 3. And case number 3 is the same integral, but I have this point and I have this point. And so this case occurs when this point here is greater than 0, so t minus b, I hope you can see, I'm flashing these pictures back and forth, and I hope I'm not confusing you. I hope you can see actually when I get there. But here's t minus b, and that's greater than 0. So case number 3 is t minus b greater than 0. You okay with that? And then also, this t must be less than a. So t must be less than a. And now I write with that in mind, I write the integral. And this goes from t minus b to t. Let me remind you of that. T minus b to t multiplied by 1. Okay? T minus b to t, that's the area of that's going to be this area under the curve, the product of those guys. Okay? And this is where it holds. So yeah, I'm gonna have to rearrange this into a t b, but that's all. Don't worry about that. Okay? And so this is b minus tau multiplied by 1 d tau. So the product of the two functions, the slant, the downward slant, the downward slope, and the 1. I don't know if that's confusing or not to put the 1 in. Probably for some of you it's confusing, and for some of you it's great. That's life. And this is b tau from tau equals t minus b to t, the lower limit and the upper limit. That's this guy integrated there. Minus, t squared over 2 from the same limits, t minus b to b. To t. Okay? So I integrate this term, and then I integrate this term, and then I have to shove in the limits of integration. This is about as messy as this is going to get. It's not that messy. bt, that's this limit here, minus b times t minus b. That's this term here. I'll make a mistake, I'm sure, on these minus signs. So this will be t squared over t, tau squared over t. So t squared over t, there's a minus sign there. And then I have a minus, minus a minus, which is t minus b squared over 2. Did I make a minus sign mistake? Okay. I'm usually good for a few minus sign mistakes in any given lecture. I know I shouldn't tell you that. Well, I should. Okay. And now I just have to crank through all this stuff. And I won't bore you with the details. And there's the answer. So again, bt minus bt plus b squared minus t squared over 2 plus t squared minus 2bt minus b squared all over 2. Sort out all the powers of t, the powers of t squared cancel actually, and the powers of t to the 0. And if you want, you can plot all that stuff out to give you a waveform that looks something like we got before. Starts low, accumulates, and then fades away. Okay? The general shape of that is as important as the details of the math. And so sometimes what you can do is if you've got these kinds of two things come out of this example. One is the details of the mathematics and the bookkeepings, and what we're trying to do. You know the intuition. We got the intuition before from the discrete time case. Now it's the detail. Now it's following the bookkeeping and the details, so that's useful at the real detail level. And then climb yourself up and say, okay, what's it look like intuitively? Well, intuitively, it's this distorted pulse. It's neither a flat line nor a triangle. It's got this quadratic in it, and it goes up and comes back down again. And so if you're doing a sort of an understanding of a system, if you're trying to figure out trying to understand a system, well, that's a pretty powerful picture that you don't need the math for. Okay? Your intuition will guide you to that. Your intuition will guide you to that just as easily as the mathematics. Okay? So now if this thing has wiggles on it, or if this thing is slightly bowed or slightly concave, you can still intuit out the answer. Okay? And that could be useful. All right. Now, 1, 2, 4, 3 problems. That's pretty much my review of convolutions. Okay? That's pretty much my review of convolutions. If you add up all that takes, we spent more than a class on that. And so one of the things I hope to do is I hope I've this afternoon I have taken away some of your fear of convolutions. I hope I've made them more accessible to you, both intuitively and physically understanding what they mean, and also giving you a little bit of mathematical tricks to handle them. Remember, the analytic math is great, right? The analytic math of continuous time functions are great, and it's very nice to have a closed form expression that describes the input and output of the output of a system in the time domain or the frequency domain. It's really nice to have that, but it's also if you can't get there because your integral tables are not powerful enough, or because you're working on the back of an envelope and you don't know it, then run to MATLAB with your tail between your legs and digitize the heck out of that system and use the discrete time case to numerically solve it. And I'm pretty sure there's a MATLAB code already on my website, stolen from Lottie, who's happy enough to sell it to you. You bought the book, so you own it. Now it's just easy to access and put it in, change whatever you need to change, and run with it. Okay? All right. We're now going to move to Fourier series. And I won't be able to do a lot with, let's see, how long do we have? Another half hour? Good. I won't be able to I can introduce Fourier series in a very funny way for you guys. Okay? And then we'll get to the calculations of it tomorrow morning at 9 o'clock. Okay? Now, before I get started on Fourier series, one of the mathematical properties of sines and cosines, one of the reasons we like them so much, is that the word is orthogonality, but I'd rather, that's just a label. I'd rather show you what orthogonality means by the mathematics. Okay, so I'm going to write down the mathematics, and the mathematics that follows gives meaning to the word orthogonal. And then we'll come back and once we know the mathematics, we'll come back and we'll take a look at what orthogonality means from a more intuitive sense. Okay? So I want to consider the integral. Cosine of n omega naught t, cosine m omega naught t. So these are two cosines. Oh, and I'm going to integrate this across t naught, and I'm going to integrate this in the time domain. And so these are two cosines. They both have a fundamental frequency, omega naught, which leads to a period, a fundamental period, capital T naught. Okay? So they both have a fundamental period, some fundamental frequency and a fundamental period, omega naught and T naught. 2 pi over T naught is equal to omega naught, and so on. Okay? Hopefully you're comfortable with that. Good. This one has harmonics. It's the nth harmonic, and this one has the nth harmonic. So they're and I'm going to integrate across that fundamental period T naught, or just as easily I could integrate across infinity. I can integrate from minus t to minus t over 2 to t over 2, and go all the way out to however long I need. But these are two cosines, and so I can get all the information if I integrate across a period. Okay? And I should point out that m and n are integers. Okay. I look at that and I first say, oh my God, that's a difficult integral to do. But then I remember one thing, and what is the one thing? Trig identities. I could do exponential. I can do e to the I omega t plus e to the n omega naught t I n omega over 2, and I can multiply all that stuff out. Absolutely true. That's a great way to do it. What I'd rather do is I'd rather do the trig identities, and then apply some intuition associated with that, because that'll sidestep some bookkeeping mathematics. So at this point, I agree you can do exponential Euler's relation, or you can use trig identities. This will lead to math, rigorous math, the same result, and this will lead to some intuition. And they'll both be the same. Okay? So, this integral, and I'm just doing some math. So I'm not going to make a big deal about this. So this is 1/2 times the integral across T naught of cosine of n plus m omega naught t dt, and then I need another 1/2 in here, cosine of n minus m omega naught t dt, and that's also over T naught. N and m are integers. Zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because they're even functions. Cosine's an even function. I'm even going to argue that I can only have to consider positive integers. Because if I have minus integers, then when I take it through the even function, they'll be positive anyway. So I'm not too stressed about that. So here's a cosine of 17 omega naught t, or cosine of 83 omega naught t, or a cosine of 127 omega naught t. And I'm integrating that cosine across a fundamental period T naught. So what's that integral going to be? It spends, let me draw it. It's a cosine. It's a cosine. I'm integrating across a period, right? So I'm going to have, for every positive, I'm going to have a negative. Averaging that across a fundamental period means that cosine, it's not squared. It's just the cosine. I took care of that squaring function with the trig identity. So this guy here is going to spend half its time above the axis. That's a big old 0. Well, that's nice. I got rid of one of my two integrals. That's really good. Now, supposing n is not equal to m here. So supposing n was 27 and m was 2. Then n minus n would be 27 minus 2, or 25. So that would be cosine of 25 omega naught t. And what would that equal? What would the integral of that equal? Still zero. Still zero. What happens is if n is less than m, so what happens if n is 3 and m is 5? So that 3 minus 5 is minus 2, but cosine of minus 2 is cosine of 2. And so that's the cosine of 2 omega naught t. And what would that be equal to if I integrate across a fundamental period? 0. So this guy breaks up into two cases, and I know, and maybe they're the same, I don't know, but if n is not equal to m, then this is also equal to 0. It spends half its time north of the axis, half of its time south of the axis, for exactly the same reasons. Right? For exactly the same reasons. Okay? So this is all very good. Now, supposing n is equal to m, so this is 127 and this is 127. So 127 minus 127 is 0. Cosine of 0 is always 1. So now I'm integrating that 1 across a 1, and I get this to be, I'm probably going to make a mistake here, t naught over 2. Right? That will be 1 dt, that integrates to t, t to t plus t naught, multiplied by a half. I think that gets to be a t naught over 2. Am I right? We're all tired after a long day, but we're almost there. We're almost there. Okay? So this is something really weird has just happened to us. Okay? Cosine of 0 dt, which is equal to 1 dt, which is equal to t naught over 2. Just filling in the math that you might want in your notebooks or on live.
So, omega naught and t is included in cosine, or is that outside?
Thank you. Let me correct. Let me put in some brackets here. I'm not sure how needed they are, but they will clear things up a lot. Is that okay?
Yes.
Okay. That probably is one of the reasons we were slow to answer, and I apologize for that. Okay. So I need you guys here. Can you imagine if you weren't here and this went live, and that would be horrible. Don't let this happen to your colleagues. I need you tomorrow. And I'll feed you tomorrow. How's that? Okay. All right. So now what we found is I start with this overlap integral. And the only time that this is non-zero happens to be when those two cosines are exactly the same. That's an incredible property. I can write three things. I can write t naught, the cosine of n omega naught t multiplied by cosine of m omega naught t. And that's equal to either 0 if n is not equal to m, or it's equal to t naught over 2 if n equals to m. I can also play this game with signs. Sine of n omega naught t, cosine of m omega naught t. Let me do one. I'm sorry. Sine of n omega naught t, sine of m omega naught t. I'll do that one. Whoops. There. dt, dt, dt. I'm not showing this, but I'll let you prove this. 0 if n is not equal to m, and t naught over 2 if n equals to m. And I should be explicit and say that's not equal to 0, even though that's sort of implied. But just to be rigorous. So if I've got two sines, this equality holds. If I've got two cosines, this case holds. If this is the case, then this is actually interesting. This is equal to all to 0 for all n and m. Okay? And the answer for that is that cosine and sine are 90 degrees out of phase. And that's where we get into this word orthogonality. These set of equations here, in other words, sine and cosines are orthogonal. Okay? Orthogonal happens when you think about vectors, they're perpendicular, they're at 90 degrees. The dot product between those two vectors will be 0, and so you can look at these integrals, if you wanted to, as dot products of a cosine and of cosine at one frequency and a cosine at another frequency. That's one interpretation of that. Okay? And with that 90 degrees, that makes sense for this cosine and the sine. They're 90 degrees out of phase, they're going to be orthogonal. Okay? You made a big question about, you had a nice question about orthonormal, about normalization. There's another word, orthonormal. I can both normalize and look at these as orthogonal. Notice how these are equal to t naught over 2. If I do something about these integrals so that this is equal to 1 instead of t naught over 2, those functions are orthonormal. Big wow. And so what that would be is I would be multiplying each of these as 2 over t naught quantity square rooted. So if they have fundamental periods, an orthonormal expansion instead of an orthogonal expansion, orthonormal expansion will be the normalized basis set, which would be the square root of 2 over t naught. Okay. Useful, maybe, if you get really tired of writing these t naughts over 2 all the time. Okay. I'm not saying that's good or bad. I'm just introducing you another vocabulary word that somebody may use, in which case you're wise to know at least where to look it up. Let me give you another example of orthogonal. Okay, this is orthogonality in the frequency space. This is orthogonality in the frequency space. Orthogonality in a time space means that there's the overlap of one time signal multiplied by the other signal is going to be 0 unless they're the same signal. They're independent. And so we practice orthogonality in the time domain in this class. When I speak, I grab the token, and I speak until somebody wants the token. When you have a question, you raise your hand, and you take the figurative token. I shut up. You speak. And that way there's no overlap between our two signals. So I own a block of time, you own a block of time, you own a block of time, you own a block of time. And so we each transmit our information, our message signal, orthogonally from each other because there's no overlap in time. The Aloha network worked that way. There was a network, a loop of networks of all these computers, and one computer would broadcast and receive, and all the others would receive, and then it would be quiet, and the other one would ask for the token. And that's an example, if you want to be fancy, wording, that's time division multiple axis. TDMA, time division multiple axis. That's orthogonality in time. Time division, multiple axis. So everybody owns a block of time and is able to broadcast on it. That's something of an inefficient way of running a channel. But it works, and it's fairly easy to code. You get to talk on a Tuesday, you get to talk on a Wednesday, I get to talk on a Thursday. Everyone's happy. We all share the same network. We all share the same channel. And don't get me wrong, that's orthogonality in time. This orthogonality This orthogonality in the communications context means that everyone can own a certain frequency and broadcast. In the FM market or the AM market for radio here in town, one radio station will buy the right to broadcast on a frequency. They buy it from the government, ultimately. The government claimed ownership of the spectrum. Story about that. They claimed ownership of the spectrum, and they sold that to the radio stations. And the radio stations now own that property, that frequency space. And so one person would propagate on one frequency, another radio station would propagate on another frequency, and there'd be no overlap of those two signals unless they were exactly the same frequency, which wouldn't happen in a particular market because of the regulation. So frequency division multiple axis. That's orthogonality in frequency. That's orthogonality in frequency. And that's another great way to run a network. Or people can share the same channel, share the same network, share the same broadcast space by owning different frequencies or by being assigned different frequencies. And there are cell phones that work by frequency. There are wireless networks that work on frequency division multiple axis that are not broadcast. When you make a decision, when you make a phone call, they see the network sees what frequencies are available, and they give you one for the purposes of you making the call. Yes.
Is there a popularized commercial term or industry term for when you use three-dimensional space?
Both time and frequency?
Yes, because the way I'm seeing this, please tell me if I'm wrong. So the time or frequency division is the different radio stations in town.
Yep.
Time division is the different shows, like the morning show versus the afternoon show versus the evening show. They only broadcast on that station.
I wouldn't think about it. I wouldn't think about the content at all. In fact, that's an interesting point. Don't think about content. A comm system to first order is completely independent of whether it's the morning show or the afternoon show or the emergency signal.
So there's no term for it.
No. I'm sure there are networks that use time and frequency, rolling frequency codes and things of that nature. But communications is a great buzzword, jargon-rich field, and I tend to try to steer students away from that. So I'm introducing these terms tentatively, just so because they are popular. Because if you remember waves and EMAG, frequency and wavelength are hop, skips, and a jump away from each other. So in the optical world, even though you're using a frequency standard, you call it WDM, wavelength division multiple axis, or wavelength division multiplexing. And it's the same thing as in fact, it's really more frequency division multiplexing than it is wavelength division multiple. But the wavelength suggests, I don't know. It came up from that. I know the people who pioneered all that, and it is what it is. Okay, so I guess I'll put underneath there WDM, DWDM, and that's optics. Okay, so if you're working in optics, people tend to use this orthogonality, and they tend to call it wavelength division multiple axis. If you're working in the wireless mode, then it's frequency division multiple axis. In the network, you have both. Your cell phones are wireless. It goes to as soon as it hits the base station, the tower, it's optics. Optics carry it, backhaul it, 90%. There's a little bit of copper left over, but optics will backhaul it and then groom it and send it across town or across the country or across the world. And once it's there, the trunk lines are all optics right now. So the two don't fight each other. The attributes of each one fit where they need to be. But in fact, while there's cell phones and cell phone networks that could use frequency division multiple access, it was looked at a lot for video content. In fact, a lot of companies looked at it for frequency for video content, video streaming to the handheld units. But really, what people use is code division multiple access, and these are orthogonal codes. So you're going to do a digital logic operation. I think it's an OR. I have to remember, I have to double check that. Of a code plus your message signal, and that will orthogonalize it. That will make one code relative to another code. And so your codes are going to, when you make a phone call on a CDMA network, code division multiple access network, there's a set of codes out there, call them 1,000 of them, call them 2,000, and you'll be assigned one of them, so your speech gets digitized into a digital signal. That digital signal will be mixed with the orthogonal code. The wavelength, the signals will be from all the cell phones will be shared on the same wavelengths, same antennas, but separated out based on the code assignments. When you're done with your call, the code gets recycled. Orthogonal codes come also from the dot product of two vectors. It's dirt simple to make orthogonal codes. One example is to start with the matrix 1, 1, 1, 0. This vector is orthogonal to that vector. Actually, let me be more careful. 1, 1, 1, minus 1. Okay? Notice that these guys are 1s, and this guy is 1, and this guy is the opposite of a 1. So I can extend this 1, 1, 1, minus 1. That's that matrix. And that sort of is this element here. Now this element here is the same matrix, 1, 1, 1, minus 1. This guy here is the same matrix, so that's a 1, 1, 1, minus 1. And then this matrix here is the opposite of it, so that's minus 1, minus 1, minus 1, 1. Do you see how I do that? And then I can go even further. Put this matrix up in here, 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 and here, or the opposite here. So that'll be a 1, 1, 1, 1. 1 minus 1, 1 minus 1, 1, 1 minus 1 minus 1, 1 minus 1 minus 1, 1, 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1 minus 1 minus 1, 1 minus 1 minus 1, 1, 1, 1, 1, 1, 1 minus 1, 1 minus 1, 1, 1 minus 1, minus 1, 1, minus 1, minus 1, 1. Those are the same matrices. Now in this lower block, I do the minus of it, minus 1, minus 1, minus 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, minus 1, 1, 1, and 1, minus 1, 1, 1, minus 1. So this is a code length of 2, this is a code length of 4, this is a code length of h. In general, h, different h, not from our transfer functions, not from our things. That's your key, that's your seed. So you start with a 1, and you grow your matrices again and again and again. And again, you can imagine a very simple algorithm to generate these matrices where each column or each row, for that matter, is an orthogonal matrix. And this is an H because it's called a Hadamard matrix. Okay. And a Hadamard matrix is really nice. It has every row and every column are orthogonal, so that's a way of generating orthogonal codes. And It's easy to seed. If I take the FFT of that image, I can think of that as an image. That matrix is an image. Then it's flat. It's fairly flat in frequency space, not perfectly, but fairly flat in frequency space. So again, it looks random, but in fact, they're orthogonal organized codes. So it's kind of cool from that perspective. Code division multiple axis has an interesting history, and I have just a couple of minutes, and I can talk to you a little bit about that. It's a good example. It was developed for military applications. It was developed for military applications because the spectrum of these codes look like noise. So if I'm using frequency division multiple axis, I generally have frequency content that gives away the transmitter and the receiver, and it's not very secure communications. If you know the signal is there, you can record it and maybe you can code break it. If you don't even know the signal is there, you don't know whether or not you don't even have something to try to break the code on. And so code division multiple axis code division multiple axis was developed for the military, and then it was transported into the civilian life, and they needed a test bed for it, and so they picked a whole separate country to roll out CDMA for testing. And because of the relationship from a military perspective, they picked South Korea. So we're still at war with North Korea. We're still very much an ally. The U.S. is still very much an ally with South Korea. And so we rolled it. And South Korea is actually a really interesting situation. It's small, but it's 40 million people, so it's not small. And it's very, very rugged terrain if you've been there. Do we have any? No, is anyone Korean? Okay, it's beautiful. It's a beautiful country. It's very rugged, and the cities are very dense. And there aren't very many of them because there's only a certain place where you can put cities because it's so rugged. And so it's a great geography to roll out of for a challenging field test of a technology. And the Koreans loved the fact that they were going to be on the leading edge of technology, and certainly that it was nice. It was a nice relationship from a military transition to civilian transition, and so they did. They went ahead and improved it, and then we re-imported it back into the United States, and that's the nature of it. Now, a couple of other things. Does the name Hedy Lamarr mean anything to anybody? Hedy Lamarr. Who was Hedy Lamarr?
The famous actress.
She's a famous actress. She was a beautiful starlet. You know, she was also brilliant, and she's one of the inventors of record for CDMA for spread spectrum. So it's kind of interesting, you know. And she developed it playing the piano at a party. Different code keys, different frequency assignments given out and traded off, and canceling off. So she took her art and she made it back into engineering. Okay. You know, the folks that brought you CDMA went through all the decades of field testing, brought it back in. Very, 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 very wealthy. So again, coding, advanced theory for coding, created a great technology that we all hold in our pockets, and created tremendous amount of wealth for the inventors. And that's one of the greatest things about communication, is the opportunity to help mankind and help as well ourselves. Okay? All right. I think the last little bit was cut off. I apologize. Tomorrow, we will continue using orthogonality for Fourier series. So I'll begin that lecture at 9 o'clock, and we'll go for it, and we'll then at 10:30, and then at 1 and 2. So the way I'm looking at this is we've got Fourier series and Fourier transforms. That'll knock off most of the morning. maybe a little bit into the afternoon if I'm slow and patient with things. And then in the afternoon, we'll start to look at modulation and a little bit of